Yes. Uh, Good morning, or good morning, everybody. This is Masashi Kawasaki, moderator for today's lecture by Professor Takagi. First, Professor Takagi has provided you in a chat that you can download the slides which Takagi Sensei will be using. So you can download it. And the second announcement is that while the lecture is going on, you can post your question on the chat. And if I see or if Takagi Sensei, Professor Takagi sees it, occasionally he can respond. Nonetheless, we have 75 minutes for the lecture plus 45 minutes for question and answers and discussion. So total gonna be 2 hours. So if you post your question, either Professor Takagi can respond immediately, or we can bring these questions to the last part of the discussion session. All right? Okay, so Professor Takagi, please start your lecture. Thank you.
Okay, so good morning, everybody, and thank you very much, Mark and Kawasaki Sensei, for introduction. Okay. Again, they don't respond. Okay. Okay, so somehow yesterday I was, very slow. I'm sorry, and I couldn't, cover all kind of prepared. So I could, spoke to Triangle Laris, but Mr. Kagome Laris. So therefore, I start, from Kagome Laris today, and I'm gonna shrink second part substantially. And today I'm going to talk about only spin orbital motor insulator and to the Kitaev, quantum spin liquid. And if time allows, I'm going to talk about some relevant topics related to another way to quantum spin liquid. Okay, so let me flash quickly what I talked yesterday. So first, I introduced anti-ferromagnetic ordering. It's not very robust, stable against quantum fluctuation. And my logic start from here. Compared with energy of singlet anti-ferro state for two spins, has higher energy. Okay, so therefore those anti-ferro, up and down is unstable against a mixture of down up, called quantum fluctuation. And I told you in case of 1D, apparently anti-ferro is kind of a disfavored, and the quantum spin liquid is favored. But going to higher dimension, 2D, okay, because number of bond increases, right? So therefore, this antibonding bond gains energy less. However, in two dimension, you have more bond. And in general, those anti-ferro state is stabilized in higher dimension. For example, in case of squared lattice, we have 4 neighbors. Okay, so therefore the energy gain kind of doubled, but the energy for singlet, because one spin can form only one singlet. So this energy gain for singlet state is always scaled by number of spins. Okay, irrelevant to number of bond. Okay, because of that, Okay, in case of scared lattice, anti-ferro state is kind of stabilized. But Phil Anderson proposed, but this is not always true for 2D case. And for example, if we have triangular lattice, okay, among 3 bonds on top of a triangle, 2 gains energy and 1 loses energy because of geometrical frustration. As a result, you can gain only 1/3 of anti-ferro coupling energy. And because of that, on a triangular lattice, those singlet quantum fluctuation could be stabilized. And as a result, as a ground state, Anderson kind of proposed, we can have so-called quantum spin liquid state, often called the RVB state, resonance valence bond state, which you distribute singlet state over triangle lattice, but there are many ways of distributing singlet, and you have quantum mechanical superposition of those state, and at the end of the day, symmetry is not blocked. And you can have, more than one kind of quantum spin liquid, like this, quantum mechanically fluctuating. Those, consisting of, kind of short range, singlet. For example, only next nearest neighbor. Or you can have, singlet, over long distance, long range, singlet. And maybe you can clarify those into 2 categories: short range RVB and the long range RVB. And the difference of those 2 shows up in the excitation spectrum. Okay, those you need a finite energy to break up singlet, but those you might need only 0 energy, gapless, to break up pairs. And in fact, in the RVB quantum spin liquid, state, you have, excitation called spinon, carrying, spin 1/2 and fermionic. And this is kind of in contrast to conventional magnet with, S equal 1, bosonic excitation, and showing, well-defined energy versus momentum relationship called magnon, like phonon. Okay, so you have particle called spinon, fermions, and sometimes you have gap, sometimes gapless, and you have particle Hall excitation of those spinons, and in excitation spectrum, since if you introduce like a neutron kind of X-ray and create the S equal excitation, they kind of split into 2 spinons. And as a result, you have widely split spinon continuum in the excitation spectrum. So this continuum is hallmark of fractionalization of S equal 1 spin into 2 spin 1/2 excitation called spinon. And in case of short range, you have gap, and in case of long range RVB, you don't have gap, and in some cases you can have Fermi surface of spinons, and system might behave like metal in terms of thermal excitation, although they are insulator. Okay. So let's realize, those, quantum spin liquid, state, and detect such, exotic excitation called spinons. Okay, that was the story yesterday. And as best known example, I introduced organic complex, salt, which, host spin one half, triangular lattice. Okay, and their interaction scale is, something like, 180 to 200 degree Kelvin. Okay, so in the mean field, you would expect magnetic ordering around 200, but they never show magnetic ordering down to, say, like 30 millikelvin, 0.03 Kelvin. Okay, that's why people believe quantum spin liquid state is kind of realized. Okay, so the physics, I discussed, appear to be realized in those, organic complex salt, S equal 1/2 triangular lattice, magnet. And to our surprise, okay, they are insulator, but nevertheless, they behave like, metal. Okay, and for example, you have, finite susceptibility at T equals 0 limit, like Pauli susceptibility, and you do see T-linear susceptibility, T-linear specific heat called gamma, okay, down to T equals 0 limit, like metal. And the ratio of, chi and gamma should be kind of universal constant, called the Wilson ratio, and they satisfy the, Wilson ratio, by factor of 1.5. So just taking a look at susceptibility and specific heat, they look like just, simple metal with Fermi surface and a finite, density of state. But of course, they are insulator, and so therefore, you might take this as, kind of a spin-on Fermi surface. And even, big surprise is, this data, thermal conductivity divided by temperature. And this, quantity is, scaled by C over T, that's like, gamma times mean free path of, excitation carrying heat. And you do see, finite, intercept, which means you have kind of a T-linear term. Okay, so that's consistent with the presence of T-linear specific heat. But the point is, from this data, you can estimate mean free path is, of the order of 1 micron. So that means, there is, Fermi surface carrying heat, but doesn't carry charge. Okay, doesn't carry charge. But that excitation is, quite mobile, over 1 micron. Okay, but unfortunately, organics, you cannot do neutron, scattering measurement to detect continuum, like, one-dimensional anti-ferromagnet. And recently, people went to inorganics, where you can do neutron measurement. And at the moment, most, studied system is Ytterbium-based system, which, carries J effective 1/2, equivalent to spin 1/2, moment on top of triangular lattice. And as I showed you yesterday, here is a neutron result. And you see quite, broad, excitation over Q space and over different energy. So you see kind of spread of excitation. And this, seems to suggest the presence of continuum excitation. Okay, but unfortunately, at the moment, we haven't reached the end of story. At the moment, there is kind of ongoing debate. What is origin of those, continuum? Is this, kind of spin-on continuum? Or, many people now, start, pointing out disorder induces some sort of random distribution of, spin singlet, static spin singlet state that, could account this, continuum. So in that sense, because of disorder, unfortunately, we are both there, but we haven't reached, final stage of identification of spin-on yet in triangular rallies. Okay, that was the kind of status. And another interesting playground arena to search for quantum spin liquid and perhaps spin-on physics is Kagome rallies. And so this is Kagome rallies, and you immediately notice each spin 1/2 has 1, 2, 3, 4 bond. Remember, triangular rallies, they have 6, okay? But now, we have only 4 bond. So that means, anti-ferro state, anti-ferromagnetic ordering is, much more unstable than the case for triangular rallies. So therefore, Kagome rallies, we have, by far better chance of finding quantum spin liquid. That's the understanding, okay? And theoretically, because of, less number of bond, Kagome anti-ferromagnet has been studied a lot. In the last, 10, 20 years, numerically, or, by back of envelope, calculation. And as you see from this view graph, I cannot, get into details of those arguments, but there is a big, fight, or not, I shouldn't say fight. There is a big discussion among, theorists. And some theorists saying, this ground, state should have, gap, J called G2 quantum spin liquid, which is gapped. Okay, so that means perhaps those singlet is kind of relatively short range. But other people saying it has fallen into so-called U1 symmetry, and the excitation gapless, like Dirac dispersion. So you have like a Fermi point, okay, like Dirac electrons in graphene, okay, and but since this has completely different symmetry. For theorists, this difference it's not small, but quite critical. And at the moment, theoretically, there are kind of 2 camps at the moment. Okay, and yesterday I remember there was a question, how this short range RVB and long range RVB, can be realized. Okay, or which distinguish short range RVB and long range RVB. And my answer was, I'm sorry, I'm not sophisticated, and I cannot answer that. But as you see, in fact, this is kind of my excuse. Even on same lattice, Kagome, those gapless spin liquid and gapped spin liquid has very close energy. In terms of energy, they are very close, and it's kind of hard to distinguish which one is which. Okay, So therefore, it's kind of a hard to, what is, realizing, what kind of quantum spin liquid. Okay, that's kind of my excuse for the question yesterday. But anyway, so because of that, realization of, Kagome was, very much interested. And the first, they want to see quantum liquid in the state. And second, can we see gap in the excitation or not? Okay. That was, quite important issue. And at the moment, the biggest star in this Kagome community is a compound. Okay, this is kind of mineral compound called Harvard, smithite. Okay, so this is the name of mineral made of zinc, which is non-magnetic, and copper, and the copper 2 plus, carrying spin 1/2. And in their structure, you find the Kagome layer made of copper 2 plus and the zinc and copper. Okay. And this is kind of nothing but this structural chemistry I mentioned yesterday. So this pyrochloride, from 111 direction can be viewed as piling up over triangular lattice and Kagome lattice, and they put copper for this Kagome layer and put zinc on top of triangular lattice. That's why you can isolate 2D spin 1/2 plane in those compounds. Okay, and unfortunately, again there is issue of some disorder. This triangular lattice is supposed to be 100% zinc, but experimentally people observe something like 10-15% of zinc is replaced by copper in this layer. That's but that's clean physics a little bit. Okay, but anyway, so this compound from susceptibility, Curie wise, okay, scale of anti-ferromagnetic interaction, something like 200K, 180K. But nevertheless, down to less than 1K, you don't see any signature of magnetic ordering, like in neutron scattering, susceptibility, specific heat. That's why people claimed this compound should be quantum spin liquid. And this is kind of inorganics. And Yon-San Lee, he's now in Stanford, but that time he was in MIT. He did extensive neutron measurement, inelastic measurement. And this is kind of a similar picture as ytterbium compound. Okay, and this shows the distribution of excitation in Q space. And you see quite broad excitation. Okay, over different energy scales, something like 1 to 6 milli electron volt. Overall kind of energy scale of interaction is 50 milli electron volt. So it's quite broad. And in fact, if you have cut over energy versus Q, you see where they find the continuum excitation. So they claim this, as evidence for spin-on like continuum excitation. And they kind of integrated those neutron response over large energy region. And if you integrate the intensity over energy, that means instantaneous correlation. So this is kind of an instantaneous correlation. And this bottom figure, E, is a kind of a calculation of kind of a correlation based on random distribution of singlet spin pairs. Okay, nearest neighbor short range, spin pairs. Okay. And first of all, you can see pattern is, quite similar. But in experimental, instantaneous correlation, somehow distribution is, narrower than the calculation. And the calculation considers only short range. And they discuss, somehow in principle, randomly distributed spin singlet is kind of correct. However, there are, a spatial extent of singlet is kind of long ranged rather than, only nearest neighbor. Okay, so you have kind of a medium, range, kind of a, singlet pair in real space, and that's kind of a nothing but picture of RVB state. Okay, so that's kind of quite a beautiful experiment. And then next question is low energy excitation, whether we have gap or not. But unfortunately, as I said, there is some mixture of kappa into normal zinc, and there is some low-lying excitation from impurity, and that bad for neutrons kind of scattering measurement. And recently, people went to NMR, and NMR you can measure susceptibility at the site far away from magnetic impurity. So you can measure intrinsic susceptibility, okay, using NMR. And this is night shift, intrinsic magnetic susceptibility. And you can see susceptibility goes down very quickly. And this black point is kind of low field data. Okay, and somehow, susceptibility decays very rapidly at low temperature, and followed the exponential decay. And from this behavior, kind of they concluded that there must be an excitation gap of the order of 10K. And in fact, if you apply field, singlet, state, spinor excitation could be kind of stabilized by Gma energy. And in fact, this, gap, at low temperature, it kind of suppressed, and eventually disappears. And from that, they concluded, there is, gap of the 10K, and it's, gapped, G2 quantum spin liquid. And there is a sister compound, essentially same structure, and the other group using a fluorine NMR reached the same conclusion. And so, like 2 years ago, we thought, okay, Kagome, it's kind of done, but recently, again, some question you put to this NMR kind of study. Okay, so this is quite a recent, paper on NMR, and this is kind of comparison of all the NMR and the latest NMR. Gross feature, they're the same, but at low temperature, new data, decays slowly, and okay, so this, white is old data, claim the exponential decay, but the new data appear to decay almost linear in T. And because of a T linear decay, they suggested that, the spinor excitation is kind of a gapless, and like, U1 Dirac, quantum spin liquid. That's, what, they claimed. And because of that, unfortunately, I'm sorry, I'm always, ambiguous about, conclusion, but, experimentally, the issue of gap hasn't been solved yet. I think that's kind of a fair kind of statement at this stage. And there is other Kagome compound recently showed up. It's kind of a double layered Kagome system. And in this case, magnetic interaction is very small, like 2K, but down to at least 50 milli-K, no magnetic ordering, like a susceptibility, muon spin rotation. And because of the absence of magnetic ordering, this compound was claimed to be quantum spin liquid. And again, neutron scattering measurement, was done. Okay, and they observed, kind of beautiful kind of continuum. Okay, like Hubbard's missile. Okay, and they observed T-linear specific heat at low temperature, and claimed ground state. You have spin-on Fermi surface, and you have excitation, like metal. Okay, but unfortunately, if you measure thermal conductivity instead of specific heat, as you see, T-linear term is lacking. Okay, so there seems to be continuous excitation at omega equals 0, but those excitation appears not itinerant. They are not mobile. So in that sense, again disorder might play a role. So it's quite interesting, but we haven't reached final conclusion for the existence of mobile spin-on Fermi surface. That's kind of a current status of Kagome. Okay, but of course you may say, okay, somehow always disorder bothers, and it's not 100% clear. We do see mobile spin-ons in those triangular or Kagome magnet. Yeah, that's true. And as an experimentalist, I have to admit, we have many things to do kind of experimentally. But on the other hand, compared with say like 10 years ago, we got surprisingly large progress in this field. 10 years ago, we discussed only absence of magnetic ordering. But now, we start seeing all those kind of excitation, kind of spin-on-like. And of course, there is kind of some ambiguity. Okay, but certainly we do see a kind of big progress, and it's good. We have many things to do in future. Okay, but anyway, so far those RVB state, as I said, we never obtain RVB state as exact solution of a relevant Hamiltonian, except for very special, not realistic case. And because of that, there is a big kind of ambiguity, like a Kagome case. We don't know whether there is a gap or not. Okay, but recently, new route to quantum spin liquid is kind of proposed by Kitaev, and it turned out to be it is big breakthrough in the field of quantum magnetism, because Kitaev solved his modular Hamiltonian, and quantum spin liquid was successfully obtained as exact solution of one Hamiltonian. So now in the equation, we see kind of what it is. So theoretically, it's kind of real. Okay, so that's kind of a new emergent field. And let me introduce, what is Kitaev, quantum spin liquid. Okay. So this is called the Kittek model, and that's kind of quite simple but elegant model. So Kittek considered the honeycomb lattice, okay, so bipartite lattice, and placed spin 1/2 moment on top of honeycomb lattice. So you have spin 1/2 in honeycomb lattice, and each spin 1/2 moment is connected by eyeging. Eyeging means interacting only for one direction, one component of spins. Okay, and we have 120-degree 3 bond on honeycomb lattice, and each bond gives rise to aging interaction for X and Y and G. So that means this bond, okay, two spin can gain energy, when spins are oriented, X direction and the ferromagnetic, and this direction, aging axis is kind of Y. So therefore, those bonds, if spins are orienting Y direction, ferromagnetic, they can gain energy, and the G bond, okay. When spins are orienting G direction ferromagnetic, you can get energy, right? So you have kind of 3 colors of bond, okay? Blue, red, green, and you have ordered distribution of those 3 colors on top of honeycomb lattice. Now, so focusing on this spin on this side. Okay, this bond, try to polarize spin X direction. And this bond try to polarize spin for Y direction. And this spin, G direction. But those 3 are kind of orthogonal to each other. Okay, so therefore, those 3 bonds kind of compete with each other. And this spin kind of frustrated. Okay, so they want to satisfy X bond, they cannot satisfy YG. If they satisfy Y, they cannot satisfy X and G. Okay, and as a result, quantum spin liquid is kind of realized. Okay, so that's quite a nice picture. Okay, and this I got some criticism from theorists. That's not exact, but in order to give you kind of some image, let me give you this. Like maybe this quantum spin liquid state, we might have some sort of RVB like picture. So like each spin make Ising ferro bond, like a singlet bond, and you distribute this ferro Ising mode bond over kind of space, but there are many ways of distributing satisfied bond, and you have kind of a superposition of different distribution bonds. So in that sense, I can see some relevance to RVP kind of physics. But the beauty of this model kind of beyond the RVP quantum spin liquid, it's you can solve Hamiltonian using so-called Majorana language, and you can show the ground state. It's quantum spin liquid with ensemble of 2 type of Majorana fermions. Okay, so again this is kind of a model, and you can define some quantity called G2 flux. That is kind of a product of okay. So you have this. You have G bond, okay, X bond, okay, and blue bond, right? So you have kind of a product of G, X, Y in rotation, and this is called a G2 flux. Okay, so you make a kind of loop, and this defines a kind of gauge flux. And this, quantity kind of this W commutes with Hamiltonian, and so they have, eigenvalue of plus minus one. So using a plus minus one, you can express, state n. Okay, and this, flux, at the end of the day, in the ground state is kind of a uniform, and that's kind of quite important to solve this. And so this Kitayuki Hamiltonian with Ising interaction, okay, Kitayef, introduced, Majorana operator or spin operator. So he divided, spin operator into two kind of Majorana operator, B and the C, and the B has kind of three kind. Okay, X bond, you have, BX, Y bond, BY, G bond, BG, and C is, called, matter Majorana fermion, and at the end of the day, that become, iterant. So they kind of, he kind of decomposed the spin into two kind of Majorana fermions, and using this, mathematical expression, this Hamiltonian, it's simply replaced, by this. Okay, and this Uij, comes from this bond, Majorana fermion operator, and this again commutes with Hamiltonian, and they have, eigenvalue of plus minus I. Okay, so therefore, there is a CICJ, and this because this is kind of Majorana operator, so Ci equals C dagger, right? So therefore, if you take this as kind of a transfer, this is nothing but tight binding Hamiltonian. Okay, so this sets, kind of Hamiltonian describing motion of C Majorana fermions. And as I said, in the ground state, flux, orders, and those U takes a uniform value. Then this is kind of a constant, and this Hamiltonian is, nothing but, a tight binding Hamiltonian for graphene. So therefore, in the ground state, you have, Dirac dispersion of this C operators, so that kind of give rise to kind of a ground state. So therefore, you have, iterant, Majorana in the ground, state, which, Dirac-like dispersion, gapless. And you have, flux, ordering. That sector is, gapped. But this flux, ordered state, which, Dirac dispersion is, ground state of this Hamiltonian. And that, consists of Majorana. Okay? And in fact, this fractionalization of spins into two kinds of Majorana. Okay, this case, it's not, spinons, but it's, fractionalization into two kinds of Majorana. You can see it in a specific heat. Okay, so this is a specific heat for, Kitayef model calculated by, Motome and co-workers. Okay, and this, temperature is scaled by Kitayef interaction K. Okay, and as you see, you have, two peaks in specific heat. Okay, one is, over the order of K. So like over the order of K, spins, start correlating each other. That's why, there is entropy change, and you have specific peak. And at, very low temperature, okay, at very low temperature, okay, like, 1% to 0.1% of, K, you see a huge peak. And they say, this is related to flux ordering. So this G2 flux become uniform over the space. And that gives rise to Dirac-like dispersion. And this peak if you calculate the entropy, carries 50% of R log 2. Okay, and 50% means a lot, right? So we have, spin Warhouse spins with an entropy of kV log 2. But now, spin fractionalize into two kind of Majorana, itinerant and localized. And this is kind of ordering of a localized. Okay, so this peak with 50% means this localized Majorana carries, 1/2 of entropy. So this kind of two peak and 50% entropy represents fractionalization of spins into Majorana. Okay, so that's the physics. But anyway, somehow, in many of condensed matter field, people are looking for Majorana, but somehow this quantum spin liquid business, suddenly, Majorana particle shows up, okay, in the ground state of quantum spin liquid, and this is kind of exactly solvable Hamiltonian, and we know what it is, and the people got excited, and the experimentalists want to materialize this honeycomb quantum spin liquid state. And it turned out using heavy transition metal oxide like iridium ruthenium, we can design Kitaev model in a real material. And again, we still have some reservation, but in the other material, we might have seen Kitaev quantum spin liquid, and hopefully Majorana fermions. Okay, that's kind of story I want to tell you from now on, using remaining minutes. Okay. And how to materialize this Kitaev quantum spin liquid state? Okay, and to kind of convince you, I have to start from interplay of electron correlation and the spin-orbit coupling. Okay, so in case of Heisenberg magnet, once you have a kind of structure, in many cases, interaction is kind of a Heisenberg-like, and in terms of materialization, it was easier to see. But this case, we have to create, bond-dependent Ising interaction, and you have, 3 color, and you have to distribute 3 color homogeneously over the space. That need some technology, and some technology is hidden in the spin-orbit coupling. Okay, so somehow we handle kind of strange compound like iridium or ruthenium rather than copper, nickel here, and those compound they're kind of heavy element. And the spin-orbit coupling is kind of relativistic effect, and people know spin-orbit coupling is quite large. And in fact, in the textbook, they say spin-orbit coupling is scaled by g, atomic number to the 4th. Okay, but by calculating based on this, spin-orbit coupling kind of too large for 4D, 5D. But recently, Daniel Komsky educated me, and he told me actually Landau gave a kind of correct answer, and there is some magic inside an atom, and this spin-orbit coupling should be scaled by atomic number squared. And because of that, this ion, spin coupling is, known to be something like of the order of 30 millectron volt, something like room temperature. But, for the ruthenium, atomic number is, roughly kind of doubled. And you have, 100 millectron volt lambda. And if you go 5D, okay, now you have, factor of 3 larger. So therefore, spin coupling is one order of magnitude kind of larger. And for 5D, as you see, spin coupling is over the order of 500 millectron volt. Let me say 0.5 electron volt. So if you take a look at the hierarchy of relevant energy scale, like Coulomb nu, crystal field splitting, spirit coupling lambda. In case of 3D, we have very clear hierarchy among those parameters. But for 5D, this lambda is kind of more than factor of 10, larger, and as a result, okay, what's happening is Coulomb nu is kind of reduced to 2 to 3 electron volt, and in the crystal field splitting is 0.1 to 3, and spirit coupling is something like 0.5. So somehow for 5D, all kind of important parameter characterizing electronic state is all around the 1 electron volt. Okay, so you cannot see clear-cut hierarchy, and you can expect interplay between them. And this such interplay is key to realize equitable model in a real material. Okay, and this importance of spirit coupling and the electron correlation was first recognized in layered perovskite compound, strontium 2 iridium O4. Okay, crystal structure like lanthanum 2 kappa O4, mother compound of high TC cuprate. Okay, and if you take a look at the periodic table, iridium is here, rhodium here, cobalt here. Okay, so they have same d electron number. So in a 214, they should be 4 plus, and they have 5 d electron. Okay, so the same 5 d electron. And normally, from 3D to 5D, d orbital in space gets bigger and bigger. That means transfer should increase. So system becomes more and more itinerant from 3D to 5D. And in fact, strontium cobaltite is a ferromagnetic metal, and rhodate is no magnetism, just paramagnetic metal. And so therefore, for 5D strontium iridate, you would expect just a boring paramagnetic metal because of weak correlation. But somehow, experimentally, we find strontium iridate insulating and magnetic ordering. And this strontium iridate appear to be magnetic mode insulator. It was a big mystery, but my young colleague, BJ Kim, at the time, he solved this issue, and he pointed out spirit coupling is in charge of mode state for strontium 2 iridium O4. So now we have 5d electrons in T2G orbital for iridium 4 plus. Okay, so you have 1 4 here. And the T2G triply degenerate. So therefore, this 1 4 is shared by 3 orbitals. That reduces effective Coulomb energy. So therefore, without strong spin coupling, you do expect, boring metallic state. But as I said, spin coupling for iridium is quite big, of the order of half electron volt, larger than crystal field splitting. And it is known T2G orbital can be treated as p orbital. Okay, L equal 1 p orbital, but sign is kind of minus. Okay, so therefore, with strong spin coupling, those triply degenerate state split into J1/2. Okay, orbital moment and spin moment antiparallel, and spin moment and orbital moment parallel. Okay, so this is kind of quartet, and this is kind of doublet. Okay, so one hole or one electron is located in this split J1/2 band. So unlike this, now you have only one electron per band per orbital situation. So therefore, with modest spin orbit coupling, you can have multi-insulating state. And yeah. And so if you have multi-insulator of J1 band, this localized spin should have this wave function. You can easily calculate this. Okay, and this has equal mixture of xy, yg, and gx. Okay, and there is imaginary index I representing orbital motion of electrons around the nuclei. Or other way of taking a look at it, this part is LG equals 0 and upspin, and this one is LG equals +1 and spin down. But anyway, so it's a complicated mixture of upspin and downspin, and you can view this J1/2 state as spin orbital complex. And using X-ray inelastic scattering, we can have spectroscopic proof of J1/2 state realized in strontium iridate. And as this J1 film moment behave like a spin 1/2. Okay, so that's important for quantum spin liquid. But it has kind of internal structure, made of orbital and spins, and you have opposite spins residing on a different orbital state. So therefore, coupling between J1 moment is quite complicated and quite sensitive to bond. Okay, because those orbitals are quite anisotropic. And if you have perovskite like Laris, octahedron is connected by 180-degree bond. Because of equal superposition of x, y, y, g, gx, system is just like Heisenberg. And in fact, this strontium iridate behave like lanthanum cupellate, Heisenberg magnet. But now the point is here. So if you have H shared bond like this, the coupling is quite anisotropic, and you are supposed to have ferromagnetic coupling only when spins are perpendicular to the plane. Okay. Now you see essential ingredient of Kitaev model here. Okay. So the reason why we have aging like bond comes from here. Okay. So like we have one hole in J effective 1 localized, and now we consider exchange interaction. And conventional exchange is hopping between neighboring J1 half. Okay, but because you have two super exchange paths. Okay, you have kind of a two auction in between J1 half moment, and those two auction, okay, has kind of two paths interfering each other, and because of quantum interference of those two paths, this direct hopping from J1 half to J1 half is prohibited. So therefore, exchange is dominated by hopping from J1 half to J3 half. Okay, so J1 half hop into J3 half, particularly JG called 3 half state. And in this configuration, you have Funz coupling, connecting this pseudo spin and J1 half spin, and because of Funz coupling with JG3 half moment, this coupling become Ising. That's why for this coupling, you have Ising coupling of J1 half spin. Now, once we understand, if we have kind of edge sharing, there is Ising bond within Ising axis perpendicular to bonding plane. And as you see, for octahedron, perovskite like octahedron, you have three parallel edges. Okay. 1, 2, 3, and as you see, those kind of three edges are orthogonal to each other. Okay, perpendicular to each other. So therefore, if you connect, okay, 3 octahedron to 1 octahedron by edge, okay, so you have 3 edge bond, okay, and those bonding plane is perpendicular to each other, and you have kind of 3 bond 120 degree like honeycomb lattice, and bonding plane are perpendicular to each other. So therefore, this special exchange process of a J1 moment should give rise to Ising coupling between planes, 1x, 1y, 1g, red, blue, green. That's essential ingredient of Kitagami model. And if you connect those 120 degree bond, you can form honeycomb lattice, right? So if you have honeycomb network of such edge shared octahedron like this, okay, and if this super exchange process dominates, your material represents Kitagami model. Okay, that's how you can materialize Kitagami model into material. Okay, and this was first noticed by my colleague George Jacqueline and Gignat Caviolin. And fortunately, there are number of compounds with layered honeycomb plane, okay, listed like this. So they have edge shared octahedron with iridium 4 plus or ruthenium 3 plus, D5, J1 half, and isolated by, for example, alkali ion, hydrogen, like this. Or we can have even a 3-dimensional version of honeycomb lattice, called honeycomb. So there are a number of compounds closely linked honeycomb Kitagami model. Okay, But unfortunately, you know, there are many compounds kind of discovered or proposed. But as you see in the specific data, at low temperature, for almost all the compound, you see well-defined lambda like peak and anomaly in magnetic susceptibility. So therefore, all proposed, unfortunately, have long range ordering. And long range ordering is either this zigzag ordering or spiral like ordering. And people believe in a real material we have interaction on top of KTF interaction, and those additional interaction stabilize magnetic ordering, either zigzag or spiral. So unfortunately, many of those compounds, KTF quantum spin liquid is not realized. But there are exceptions. One is hydrogen iridate, okay, with interlayer hydrogen, and ruthenium chloride, okay, honeycomb ruthenium chloride, and magnetic field. And so that's kind of materials of interest in terms of KTF physics. And using the remaining minutes, let me go through those. Okay, so this is hydrogen honeycomb compound replacing lithium with hydrogen, and this is kind of NMR like organic. And as you see, there is no kind of a broadening of NMR peak, okay, down to 1K. By the way, the energy scale of interaction is over the order of 100 to 200. So this is 0.01 J, okay, 1% of energy scale of interaction. And this is night shift, like Kagome compound. And you see Curie-wise like behavior, and decaying kind of gradually, and go to kind of finite value. But again, you don't see any kind of signature of magnetic ordering. And because of the absence of magnetic ordering, quantum spin liquid state is kind of highly likely. But in terms of excitation, at low temperature, we do see only T-cubed behavior of specific heat, no T-linear specific heat. So therefore, this hydrogen honeycomb is quantum spin liquid. But since at low temperature, we don't have any kind of continuous magnetic excitation. So excitation seems to be gapped. Okay. And as I said, for pure KTF spin liquid at low temperature, you are supposed to see anomaly in specific heat associated with ordering of flux. But somehow, we don't see that. So in that sense, this hydrogen honeycomb, we are sure it's quantum spin liquid, but relevance to KTF remains elusive. And in parallel, other star compound showed up in this community, ruthenium chloride. Okay, so ruthenium is 3+. Okay, but ruthenium has 1 electron less, so therefore they have 5d electron like iridium 4+. Okay, and the ground state is kind of a J1/2, and they form corner shared honeycomb lattice of a ruthenium chloride octahedron, edge shared. So that mimics KTF model. And the interlayer is kind of a vacuum, nothing there. Okay. And under zero field, okay, So you do see magnetic ordering in a kind of zigzag, magnetic ordering. So you do see clear, magnetic peak associated with magnetic ordering, and susceptibility shows kink. Okay, so first, people thought it's kind of one of them, but then people noticed if you apply magnetic field parallel to the honeycomb plane, okay, then this is anomaly associated magnetic ordering, okay, and this ordering term go down, and eventually under 6 Tesla, it goes away, or specific peak, suppressed, and then goes away around 7, 8, Tesla, okay, around 8 Tesla, okay. So somehow this ordering seems to disappear with application of field. But if you see magnetization there, you do see large magnetization of 0.5, 0.6. Okay, so honestly, people first thought, okay, this is kind of a field-induced ferromagnetic state. But somehow, after this, discovery, people studied this state, and people start noticing, although there's kind of big moment, but still, Kita physics robustly remains, and there could be Kita physics in this field suppressed paramagnetic region. Okay, so this is kind of a phase diagram. Okay, this is kind of susceptibility. And applying in-plane field, this magnetic ordering kind of suppressed around 8 Tesla, it disappears. And this critical region where magnetic ordering disappears. Okay. Now many groups noticed something happening there. And this looks like quantum spin liquid. For example, this is again neutron scattering, and a zero field zigzag ordered state. You can see where they find the magnon like line of excitation here. So this looks like a conventional magnet. But if you apply magnetic field and destroy magnetic ordering, those magnon like dispersion disappears, and there remains kind of continuum like excitation around the gamma point. And they say this represents continuum excitation like as a quantum spin liquid. And if you take a look at the original Kita paper, he discussed magnetic field effect. And Kita kind of mentioned, if you apply field, okay, this is kind of dispersion of C Majorana fermions. And with magnetic field, this Majorana Dirac dispersion has a gap. Okay, so the system now kind of topologically protected, and with gap, Kita kind of predicted we should have Majorana H state. Okay, so you have H current of C Majorana fermions, and there are thermal Ford effect like a quantum Ford effect should be half quantized in this value. Okay, so Kita is kind of a theorist, so he used C minus instead of KB scale over H, but to be realistic, this should be quantized value. Okay, and recently, group of Yuji Matsuda in Kyoto measured the thermal Ford effect of this ruthenium chloride system under magnetic field. And this magnetic field, like 8 Tesla, is this region where actually zigzag magnetic order disappears. And the y-axis is kappa xy over t, which should be quantized. And somehow, this is kind of very narrow region of field, but somehow this value is very close to the predicted value of quantized contribution from Majorana edge state. And somehow this region still inherit Kitaev physics, and seems to have Majorana edge. That was clear. But somehow, yeah, this is kind of beautiful, so beautiful, and but kind of nobody reproduced this result, and sometimes quite different result. But maybe so this is almost end of my lecture, so I'm allowed to show kind of my own. And recently, my colleague Jan Bruin, Ralph Klaus, they got the exactly same crystal as Matsuda from Kyoto, and they kind of measured using machine at Stuttgart. And this red is kind of Stuttgart result, and the blue is kind of a Kyoto result. And yeah, of course, it's hard to firmly state that it's kind of a quantized, but at least in terms of magnitude of kappa xy, this Stuttgart result, by Bruin and co-work reproduces Matsuda result. Okay, so in that sense, we are kind of about there, identifying Majorana fermions. Okay, now I think I have to stop now because I'm supposed to finish at 11:15. Okay, so I have some other stuff, but I can skip it. Yeah. So this I wanted to speak about another route to quantum spin liquid, and I wanted to introduce extonic quantum spin liquid. Okay. So so this is essentially the same summary as yesterday. Okay, but it could be kind of a common. Okay, and including Kitaev quantum spin liquid, I hope the audience have been convinced quantum spin liquid is one of the most exotic state of electric matter. And this is particularly my favorite because it's kind of a seemingly silent, state of nothingness, like a Zen central dogma. But there is a hidden fractionalized excitation, like spin-ons in RVD quantum spin liquid. And Majorana fermions in Kitaev quantum spin liquid. That's why I like it. And 10 years ago, it was kind of toy of a theorist, to be honest. And they lived only in the world of theorists. But now, by the effort of experimentalists, we start seeing, materialization here and there. And now we have, many compounds without, apparent magnetic ordering. We think we did a good job. We have, a bunch of compounds. And some of these compounds, we do see some signature of spin-ons Majoranus, including continuum excitation in neutron and the X-ray scattering, a finite, density of zero energy excitations like specific heat, susceptibility, thermal conductivity. So that's kind of a good news. But on the other hand, as mentioned, from topics to topic, so there are many star compounds about confirming spinons and Majoranus, but partly due to possible contribution to disorder. At the moment, we have to have some reservation to reach definite conclusion. We identified the spinons, Majoranus. Okay, that sounds like bad news, but compared with 10 years ago, as I said, we got much progress, and because of that, I believe we are about there. So if you like to join to completely or to identify spinons, Majoranus without any ambiguity, join us to search for new compound and exotic excitation. Okay, thank you very much for your attention.
Thank you very much, Professor Takagi. This lecture is open for question and discussion. And I don't see any question at the chat. Please unmute your microphone and ask question to Professor Takagi. Please go ahead. Today we have over 40 audience.
Can I ask something?
Yeah.
Hello, can you
go ahead. Yeah.
Can you hear me? Yeah. Okay. So thank you for the lecture. You showed all sorts of different experiments and signatures of supposed spin-on fluctuations in this spin liquid state. But there's always something that keeps you somewhat doubtful. And in the end, you said that you can't for sure say if it's this excitation. Maybe it's a big scale question, but what experiment or result that you will see will convince you for sure that you are seeing what you think you are seeing?
Yeah, that's kind of quite a good, question. And so as I showed, at least we see kind of a continuum excitation in a neutron scattering. And some cases we see mobile excitation and thermal conductivity. But unfortunately, at the moment, none of compound we observe both continuum in neutron and mobile excitation in thermal conductivity. So therefore, to me, first step to identify spin-on is just make a clean compound and identify continuum excitation and low energy iterant excitation from thermal transport. Or of course, in other way is as I mentioned that what Matsuda-san did, and observing kind of a topological quantized thermal Hall effect gives a kind of a direct, evidence for kind of a topological state. And I think that's kind of a, important proof, okay, without any ambiguity. And at the moment, in case of, KTF, we can expect this, quantized, thermal Hall state. But in case of RWB, quantum spin liquid, at the moment, I don't know any kind of equivalent, kind of a quantized topological state. And if, I know that, that's kind of another way of proving spin-ons. That's kind of a current understanding.
Okay, I see. Thank you very much.
Is there any other question? If you are shy, just you can type it in the chat, or you can just shout with unmuting your microphone.
Professor, I have a question.
Yes.
Yeah, so you mentioned for the Kita model, for certain bond, we need ferromagnetic coupling. Yeah.
So say it again.
For Kita model, the XXYYZZ.
Yeah, ordinary Kita model, yes, it's a fellow.
So I don't know why it cannot be antiferro.
Oh, yes, it can be antiferromagnetic.
Oh, okay. So
original model, they discussed the ferromagnetic case, but mathematically, it doesn't depend on the sign of interaction, K. And in an anti-ferromagnetic case, you can have, take a spin liquid. So only, bond-dependent Ising interaction is kind of important.
okay, so
it can be either ferro or anti-ferro.
So okay, so for a certain atom, it contains 3 bonds. Can these 3 bonds, for these 3 bonds, they can have 1 ferromagnetic and 2 antiferromagnetic. Can this happen?
Okay, you're saying can we have a mixture of ferro and antiferro?
Yeah.
That's kind of a quite a sophisticated question. Yeah, I don't think so, but I cannot explain why. So in that sense, I cannot give you a concrete answer, but I think it must be homogeneous,
Yeah, okay, I see. Thank you.
So like let me say this, like so you have 3 bonds, right? Blue, green, red, right? And general Kita model has 3 independent parameter, kx, ky, kg.
Yeah.
Okay. And so in the Kita paper, he showed the kind of a phase diagram, and actually most of the phase you have spin liquid, but when kx, ky, kg kind of equal, you have gapless excitation. But if it's quite anisotropic, as you said, they have kind of a gap. So in that sense, yeah, I never thought about sign is different. But if it is antiferromagnetic, maybe you have, gap to your spin liquid.
Yeah, I see.
Yeah.
So here we see gap. Is that mean that we have a short range RVP?
Because it's kind of icing bonds, right? So you can form a singlet, like in RVB. So in that sense, you might consider some analogy with RVB, but it's not RVB. In the sense, because of icing, you cannot form a singlet pair.
Oh, okay.
Yeah.
Yeah, I see. Thank you. Thank you.
Okay. Any other question? Then Professor Takagi, let me ask, you showed some data on ruthenium chloride, and you
Yes.
say you somehow confirm that the quantization. So
Yeah, so I think, yeah, so it's not me, but Yang Buin, but yeah, at least in terms of data, he reproduced Matsuda result.
I see.
Okay, and of course, whether you want to say this is quantized or not, it's depends how you look like data.
Yeah.
But it's not inconsistent with quantization. Yeah.
Oh, that's great. Okay, audience, young students, postdocs, do you have any other question?
Thank you very much for the lecture. And I've got a question about
Go ahead.
the other kinds of interactions that could happen in the Kitaev candidates. So in one of the slides, you've mentioned that in many candidates of quantum spin liquids, they actually showed this long-range order at low temperatures. And I was wondering what kinds of interactions could give rise to these long-range orders.
Yeah, so there are many kind actually there are kind of many kind of theories what kind of interaction give rise to this specific order, but in general, okay, like can you see PowerPoint, right?
Yes, I can.
Yeah. So like this Jacqueline Cadolin theory, considers only super exchange. Super exchange means D level hybrid with P and go D. Okay.
Yeah.
Okay. That's kind of so-called super exchange process give rise to anisotropic coupling. Okay. But of course, there is, direct exchange, process, like overlap of those, that give rise to Heisenberg type interaction. And of course, that kind of Heisenberg-like, interaction is not only nearest neighbor, but, you can have, long-range Heisenberg type interaction like J2, J3. That's also relevant. And also, in addition to this, you have, so-called orthogonal interaction. Like interaction of XX, SY, that kind of orthogonal term exists in this, class of compound. And some people are saying, that type of interaction plays quite a significant role. Okay. So at least we have, Heisenberg term, nearest neighbor, next nearest neighbor, or even higher. We have, off-diagonal term. And how strong, those interactions kind of depends on the crystal structure, lattice distortion. Yeah.
I see. Yeah. Thank you.
Yeah.
Right.
So can I ask a question?
Yes.
Yeah.
Yeah, so could you go to the ruthenium trichloride slide? So you said like you need to apply a magnetic field to break the long range order, and it has magnetic moment. So
Yeah.
like when the magnetic field is applied, the spin is not fluctuating anymore.
Yeah, if completely polarized, yes. Yeah, that's why I said the 0.6 mu b. Okay. And about 0.6 mu b is like I try to understand that it's kind of 1/3 of saturated moment, right? So therefore, with a Tesla field, 1/3 of a moment is kind of a fixed by field, but there remains 2/3 of spin degree of freedom. And the discussion is that degree of freedom gives like to type response.
Okay, so like, I mean, is it just a response from the type Hamiltonian under magnetic field?
Yeah.
Yeah. But
Yeah.
I
So of
mean,
course, the question is
yeah.
starting from type spin liquid, applying magnetic field, how robust type spin liquid state is, right?
Yeah.
And at least we know, in the weak field, this magnetic field give rise to a gap in Dirac, dispersion, and the system become topological. Because in a zero field, we have Dirac dispersion, so
Yes.
gapless. Therefore, strictly speaking, it's not topological. But under field, it become a kind of topological. Okay. And because it's kind of topological, it should be kind of a stable kind of while. But up to what Tesla, the system is kind of or spin liquid state kind of stable. Yeah, it's kind of depends on kind of details. Yeah.
Okay, I see. Thank you. And I have another question. So this is just a naive idea, but like about the in-plane magnetic field, like I think there's the 60 degrees of freedom. Like, I mean, there are possible two choice about the direction of the magnetic field, and like, does it matter in real experiment?
Actually, yeah, it doesn't matter for, in particular, this quantum Hall effect. Quanta is the thermal Hall effect. But as far as I see, this suppression of magnetism is concerned.
Right.
Yeah, as far as I know, it's not that sensitive.
Yeah, I see. That's reasonable. Yep, I understand. Thank you very much.
All right. Any other question?
Professor, I have another short
Go ahead.
question. Yeah. So about spin orbit coupling, can I go to the slide?
Yes.
Yeah. Can't see.
No, I think.
Just 30. I think.
Say stop. Okay.
I think it's slide 30.
Someone here?
Can you
which
tell
one?
the slide number?
I
You say
think 30, yeah.
30.
Yeah, around here.
Yeah. Okay.
Okay, go to the next slide.
Next. Okay.
31st. Okay.
Okay. Yes.
Okay.
Don't know, but yeah, actually, maybe not. But you mentioned that the scale orbit coupling is proportional to the charge of nuclear, the square, something like this, right?
Yeah.
Yeah, but I don't know. For this that atomic number, I think for the outshell electrons, just the can it be screened by in the electron so they don't feel the full atomic number?
I see. Yeah. So that's if I understand you correctly, that's the point of Landau. I think
okay.
you can see red underline.
Yeah.
Yeah.
Oh, okay, I see.
Yeah. So like in many textbook, they say spin coupling is scaled by g to the fourth, right? But if it is a g to the fourth, like for 5D, we should have crazy spin coupling.
Yeah.
But Landau argue, we have to consider kind of a distribution of electrons, around the nucleus, and there is, some factor which reduces spin coupling from g to the fourth to g square. So that's exactly the point. Yeah.
Yeah. Okay. Thank you.
Okay. Any other question?
I think people start leaving for lunch.
Now 33 people. Okay. So let me ask if is there any other question, or so European people start to think about lunch. Okay. So I wanna close this lecture, and we are quite happy to have over 40 audience, and we have 7 more lectures to go. And if you are interested, please join us. And Professor Takagi, thank you very much for today's lecture. It was very interesting, and I hope all the young people got a lot of knowledge from Professor Takagi's lecture. Okay, let's thank the Professor Takagi.
Thank you very much.
Thank you very much.
And see you somewhere, hopefully in Chamonix. Yeah,
all right,
that's kind of a lovely place. It's pity we missed Chamonix this year.
Next time.
Yeah. Hope.
All right. Thank you very much.
Thank you very much.